Okay, so here's where we were last time. We were talking about doing integrals in spherical coordinates. Let me remind you what we mean by this little clause here, in spherical coordinates. So it's a lot like what we were talking about doing integrals in polar coordinates. What it means is we're doing a change of variables. We're using the appropriate coordinate system as a change of variables function, doing the pullback with respect to that change of variables function, and then observing that when you do slices, once you've pulled it back into your new coordinate system space, for example, a theta slice, the way you would slice up some pullback domain in this world, those slices are perfectly visible over here in the original space that you were doing business in. Right, and so not only can you do the pullback to change the domain, you don't even really need to draw the new pullback domain. You can see all the slices you need in the place where you already have a picture. So this is what we mean by doing an integral in a coordinate system. So doing these kinds of slices adjusted appropriately, given that we're doing a change of variables, doing these kinds of slices in XYZ space is called doing an integral in spherical coordinates. Whereas, I suppose, if you really want to see the pullback, right, then you're just doing an integral in a pullback space over here. Okay. I prefer the former most of the time. A couple of details that I just glossed over. You do have to know what the stretching factor is. It's computed by the same formula that we always use. Yeah, there's a bunch of cool algebra in there, and everyone should do this once in their lives. It's a good exercise. It's a good way. It's a good little, mathematical benchmark. Are you good at trig? Right? It's tested very nicely by that algebra. So I hope everyone will, do that. Fill in that blank. It's a significant amount of trig, but like I say, it's a good exercise. Here's the answer. Don't forget that as long as you promise only to use values of phi that you wanted to use anyway, right? Then you can lose the absolute values, and the stretching factor is just rho squared sine phi. Make sure to memorize that. Okay, and then where we left off last time, your volume form, your volume differential, that you write as dx, dy, dz for rectangular coordinates. This is what it is then for integrals in spherical coordinates. Don't forget your stretching factor. Don't ever write this down without it. There's no reason to write this down by itself. Just never. Just no reason. Just don't do it. Right? Why would you do it? That's not got anything to do with the question that you were originally asked. Always write this down all at once. I think this is a really important trick to make sure that you don't, while you're distracted thinking about slices and cross sections and ranges of values and angles and leaning backwards, thinking about, so easy to forget the stretching factor. Right? Okay. All right, so we talked about all that last time. Now let's get into some examples. We've got several examples here. First one, let's suppose our domain is this ball right here. It's a ball of radius a centered at a on the z-axis. Right? So it's resting on top of the xy plane at the origin, you might say. So if that's our domain, quick moment to recognize rectangular coordinates would be a nightmare for this domain, right? Square roots everywhere, right? Just horrifying. So let's think about how to do this in spherical coordinates. Recall our slicing arrangement. We always do theta slicing first. Think about the range of values of theta. Then inside of that theta slice, we're going to look at phi slices, which inside of the theta slice look just like that. They're just little rays, measured by angle off of the z-axis, like that. And then, finally, on that phi slice of that theta slice, we look for the range of values of rho. What's the value of rho where you start? What's the value of rho where you end? So that's the sort of the picture of the game. Let's apply that here. Here's what our theta slices look like. Right? Again, theta measured as an angle off of the, let's say, the positive x portion of the xz plane. the usual theta, goes all the way around. Right? This solid it wraps all the way around a part of the z-axis. So starting and ending values of theta are easy, 0 to 2 pi. Okay. Now I have a suggestion. You don't have to do this. I think it's helpful. Technically, we're now confined to looking at this slice. The trouble is, we are looking now at this arbitrary slice, which is at an arbitrary angle from our field of view, from our perspective, right? And so the angles, now the phi angles that we're trying to understand are, we're not looking at them straight on. We're looking at them kind of from above and kind of from the side a little bit, and it's a little bbit hard to visualize. So my suggestion is to view this theta slice as having a hinge on the z-axis, as having its bottom edge on, well, that line. What are we going to call that line now? Forgive me for this, but I like to think of that as the r-axis. But there is no r-axis, right? But it's pointing in the direction where r is increasing. So it would be not outrageous within this green theta slice to think of that as being the r-axis. And so anyway, with that in mind, redraw your picture, looking at that plane straight on. There's the slice. There's that z-axis. Here's your, again, forgive me, kind of r-axis. And instead of looking at it, the way we are, look at it rather from that point of view where everything looks like it's supposed to look. So in particular then, an angle there, you don't have to worry about perspective and, right angles don't look like right angles, etc. Right? Over here, angles look like they're supposed to look. A right angle looks like a right angle. And it's just easier to visualize things. I think this is a really good idea, and I want to encourage you all to do it. It is an extra picture to draw. But remember, the purpose of a picture is to help see what you're doing. So this is for you. It's also a great way to communicate to your reader, namely your grader, what you're thinking. And again, I remind you, communicating what you're thinking about your thought, your process in analyzing the question, that's one of the big things that we grade on, right? And by the way, not just in my math class or in math classes in general, in work in general, having thoughts is nice, but being able to communicate effectively what your thoughts are to the group that you're working with, the people that you're making your presentation to, whatever, that's really important. So I think this is an important idea. It's for your benefit on the exam. It's also for your benefit in understanding the question and in many other ways. Okay, enough of that. Okay, so looking back at our picture then, let's see here. I'll go down here. Here is our theta slice that we are now looking at from a convenient point of view. We want to think about different values of phi. How many are these phi slices? Keep in mind, phi is measured off of the z-axis, like that. Okay. Well, not hard to persuade yourself that there's the lowest value of phi at 0. And we have these increasing values of phi that keep going until you have your last value of phi there at pi over 2. So we start at 0, we end at pi over 2. Yes?
How did you know that phi is measured off the z-axis, or is it just off?
That's the definition, part of the definition of spherical coordinates. Yeah, and furthermore, it's measured from the origin off of the z-axis, right? So thank you. That's a great question. That allows me to segue into my next point, which is, here's a really common mistake that students do make sometimes, and that is to look at the theta slice. Here it is. And to say, oh, right, I'm going to measure angles off of the z-axis. And, oh, look, it's a disk. I like going from the center of the disk. Look at this. We go all the way around 0 to pi. Very tempting. A lot of students will say 0 to pi for phi. And it's wrong because phi is not measured from that point. You can't just say, there's a round thing in my problem, and therefore I decree that is the origin. Right? We just can't do that. So all angles are measured off of the z-axis from the origin. Okay, how are we doing there? Everybody on board? So 0 to pi over 2. All right, last question. We're going to look now at our phi slice of the theta slice. On that slice of a slice, we want to know, where does rho start, where does rho end? Well, rho starts there. That's clearly the origin, so we start at rho equals 0. Rho ends, okay, this is the point. What do I know about that point? Well, that point's on this curve. What's that curve? Oh, hey, slow it down. That curve is really this curve. Don't forget, the second picture that we drew came from our original picture. It's really part of that surface. And that surface is clearly on the sphere. Right, and it's not the unit sphere. It's not centered at the origin. Doesn't have radius 1. Right? So you got to do some work to figure out what the equation of that sphere is. But that's, when you say this point is the upper bound, that point is on this surface, namely the sphere, and so that's the equation that tells you what you really need. This at this point is a 12.8 exercise, right? Figuring out the equation of that sphere in spherical coordinates. Step 1, write it in rectangular coordinates. Multiply it all out. Plug in known conversion identities from rectangular to spherical, and this, simplify, and then this is what you end up with. So I just glossed over a very significant amount of algebra. Make sure that you can do that. Right, that's an important part of this process. And we are now then done our range of values of theta, 0 to 2 pi. For any one of which then phi ranges from 0 to pi over 2. For any one of which then, for any pair of which phi and theta, rho then goes from 0 to 2a cosine phi. And there's our bounds. And now you can well imagine how the following could happen. All the attention that we gave to drawing pictures and thinking about slices, and it'd be a temptation to say, oh, and then the integrand, I just convert that into spherical coordinates, drop the pen, walk away, and you just forgot your stretching factor. Right? It's so easy to make that mistake. I've done it before, more times than I care to admit. And so be careful. Right? And again, if you were to take my advice and never write that down by itself, always write this down all together, that's a good hedge against forgetting. Okay. How we doing? Everybody happy? Okay. Here's another example. By the way, in case you hadn't noticed, the picture becomes really, 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 really important in these questions, right? So I just kind of took that for granted in this previous exercise we just did, and I just drew a decent picture and just enjoyed playing with it, right? And reaped the benefits of playing with the picture because I have a good picture. Make sure you can draw yourself a good picture. It is a challenge. This is not something that people are typically just born with, right? You have to practice being able to draw good pictures. I'll remind you, if you want a little short tutorial and skills to think about, things to practice while you were trying to draw good pictures, come to my office hours. I'll be happy to explain. Right? It is a non-trivial thing. There are things to think about. So anyway, I'll point out the things to be thinking about. If you feel like you're just helpless and don't know where to start on how to draw good pictures, let's talk. Okay. So next deal. Another solid ball. This one you see is centered at 1 on the y-axis and has radius of 1, square root of 1, which is 1. And so it looks like this, a hard thing to draw. And what if this was our domain? How do we slice? As previously discussed, we always do our theta slices first. That's what a theta slice looks like. Now here's a challenging little geometry question. What happens when you take a sphere, move it over, and then take an angled vertical slice that goes through one sort of vertex of it? What does that slice look like? And this is hard you got to really see things in 3 dimensions, and it's a little bit of a challenging problem. Now, I would encourage you in situations where you're on the homework and you're, face a geometric challenge like this of, what does that thing look like, and how do I see that, and am I sure I'm doing this right? Give yourself a cheat, right? In this case, my advice: buy a sack of oranges, right? And take an orange, move it over a little bit, take your handy knife, take a slice. And then having taken that slice, you can pick up and say, what just happened? What did I just do to my orange? And it's not hard to persuade yourself that slice doesn't really matter what slice you take if you think about it. And having the visual aid makes this more clear. When you have a spherical orange and you take a flat slice of any description, that cross-section's a circle, a disc. Right? So this cross-section here is like that. Yeah. Okay. And you got to think about angles. What kinds of theta slices give you what kinds of cross sections. I would suggest that as this cross section angle moves over closer to 0, the cross section slice gets smaller. Right. Again, the 3-dimensional visual aid of an orange make it easier to see this. Right? Oranges are cheap. They're healthy. Right? You should be slicing up oranges anyway. So as these slices approach the theta equals 0, I claim that's where they sort of end. Any theta further, any theta beyond 0, you're going to shave off at least a little bit of zest. Right? And the more you go, the bigger the slice is, and then eventually the slices end over here with theta equals pi. Yep.
This is still going to be a circle every value.
Yeah, and this is one of the things you'll notice about again, buy a sack of oranges, right? You take a sack of oranges, take a flat knife. It doesn't really matter how you hold the orange, and it doesn't really matter how you take all the slices that you might take off of an orange. They all give you little disc cross sections. Yep. Right, and that's just a geometric appeal. Okay. And then, by the way, you can't bring oranges into the exam or knives. Right? So this is a at-home only suggestion. But the point is that when you've seen a physical example, I mean, again, I didn't want to do this in class. I didn't want to bring a knife to class. That's weird, right? But if you do this at home and see it, then you'll remember what that looks like, and it'll help you to visualize this kind of thing without the oranges. In the future, so you'll carry the benefits with you to some degree, even on the exam. All right. Okay, so 0 to pi for theta. Then we fix a theta slice. Again, we redraw that theta slice in the way that makes it easier to look at. This cross section. Draw over there again. Not much easier to see now. Very comfortable to look at that as a circle. Right? And now we can think about the range of values of phi. What is phi doing? Hard to see the phi angles, perhaps, in this picture there, but easier to see these phi angles when you're looking at them straight on. Again, not hard to persuade yourself. The first value of phi is at 0. Certainly any slice, any phi beyond 0, you're hitting the slice, and then keep going until the last, it finally misses the orange at phi equals pi. So phi goes from 0 to pi. Yeah, how we doing? Everybody happy? The picture is essential in making sense out of this. By the way, on an exam, again, keep in mind, it's not about having the right answer on the page. It's about communicating your thought process. So I emphasize it's really important to represent your thoughts, and it'd be really, really hard to describe this in words. Right? So you almost have to draw a picture. And if you don't draw a picture, you're going to be severely handicapped in your ability to be clear in communicating your thought process. Right? So that's just what it is. Okay. All right. Okay, last question then on a phi slice of your theta slice. Where does rho start? Where does rho end? Well, rho starts at that point. That's clearly this point over here. That's clearly origin. Rho is clearly 0 there. Freebie. Right? Where does rho end? Well, rho ends at that point. What do I know about that point? That point, well, it's on that curve. Okay, well, that curve is really over here. That's what you're saying when you say it's on that curve, is it's on this sphere. And you can see the equation of the sphere right there. Of course, it's the equation because we're on the edge, we're on the boundary, so we replaced less than or equals with equals. And again, you have a section 12.8 question. You have a rectangular equation for a surface. You've got to figure out how to write that in spherical coordinates because you need to solve for rho. Right? And so take this equation, solve for rho, and this is what you're going to get. Now again, I just yada 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 a lot of algebra. That's algebra, the kind of algebra we've talked about already, so I'm going to let y'all fill in those blanks. Make sure that you can do that. It is going to be essential. It's unavoidably part of this process of doing integrals in spherical coordinates. So if you're not 100% comfortable with that, flip back. Make sure that you can do that. Come to office hours, of course, if you have questions. Okay. All right. So, again, we're all done at this point. We agreed from the start, theta goes from 0 to pi for any value of theta, phi, 0 to pi, and then on that phi slice, rho goes from there to there. Again, don't forget to write down your stretching factor. So easy to forget that stretching factor. Your answer is really, really, really wrong if you don't put in that stretching factor. It's usually worth quite a few points to put that in there. So, free money. Don't leave free money on the table. Okay. All right. Okay, last example I'm going to do in spherical coordinates. We'll go on to the next thing. This one's a really tough draw. The picture that I've drawn here is really not a thorough. It's not a. I don't know how to do better, but that doesn't mean this is good, right? So the question is, we're looking for points that are outside of this sphere. Note the greater than or equal, right? So further away from the origin than 1. So, out there. But inside, you will notice, this other sphere. So, inside the green sphere, outside of the blue sphere. And, you got to kind of look at it and figure out what does that actually mean. I like to think of this as we start with the green sphere, and then we dig out of it like with a melon baller, that chunk out of the bottom, thus revealing that what we're left with is this thing, but this picture is bad. Let me explain why this picture is bad. This picture makes it look like there's nothing down in there, but there kind of is. I mean, really, there's a lip that sort of goes around, right? I mean, if you think about it, this thing is rotationally symmetric around the z-axis, and it doesn't have corners, as I've drawn here. That's not a corner. That's a lip. It only looks like a corner because if I fill this whole thing in, it just looks like we've cut off a flat piece instead of a round piece. This is a tough draw. So, do your best and think about how to deal with the imperfections of your picture. Okay. All right, so I'm going to show you a trick on how to play this game. First step is actually not that bad. I appeal to your geometric intuition. This sphere that we started with in the first place, it's entirely encased this part of the z-axis. Even when I melon ball out the bottom, it's still entirely encasing that part of the z-axis. And so therefore, since it encases that part of the z-axis, the theta slices go all the way around. So 0 to 2 pi on the theta slices. So we move on to looking at a single theta slice. And now we face this ugly, this terrible geometric problem. How do I draw an angled slice of a solid that I could barely draw on its own? And this is hard. Here's the trick. The trick is, note you don't have to draw a slice of the hard solid. What you can do is draw instead slices of the original spheres. That's easy. This sphere here, a theta slice of that sphere is just that. Right? This sphere down here, a theta slice of that is just this. And so you can see right here on this picture, taking a slice of this remainder up here, I'm going to view it instead as just the remainder sitting in between these two original slices. And so there's a picture of our theta slice of our solid. Does everybody see how that argument went? So I kind of sidestepped the artistic challenge by doing the slices first and then removing the blue chunk, instead of removing the blue chunk as a solid and then trying to slice up this hard remaining solid. For your consideration, a tool for your toolbox. I'm not saying this will always be the move, right? But this kind of thing, look for opportunities to take advantage of. Okay. So, with this picture in mind, then let's think about, what happens on this. I guess I better draw this again. What happens on this piece? What do our phi slices look like? Well, phi is going to start there at 0. And then they end at that point, and I've got to figure out how to solve for what is phi at that point. Now, again, you could take an analytical, write down a bunch of equations and solve point of view on that. I prefer the smart alecky observation, like we've benefited from before, and that is to observe that that is a radius of that circle of radius 1. That is a radius of that same circle of radius 1. So both of these distances are clearly 1. And then this is a radius of that circle of radius 1. So that distance is 1. So we're looking at another equilateral triangle, and those angles are well understood. So how convenient. Again, it's convenient. It comes up sometimes. Be on the lookout. Right? Okay, so at that point, phi is equal to pi over 3. Okay. Okay, so the last part of the process, as usual, given a phi slice of our theta slice, we're looking at this little line segment. Where does rho start? Well, rho starts at that point. That point is on that curve. Oh, wait. That curve comes from this sphere. And I can just write down the equation of that sphere, which, of course, I'm given. That's a unit sphere, so that is rho equals 1. Okay. Second part of the problem says, where does rho end? Well, it ends at that point. That point's on this curve. Oh, wait a minute. That curve comes from this sphere. And so, again, you've got to do some algebra. Got to do some 12.8 algebra and trig. convert from rectangular coordinates to spherical coordinates, but you can solve for rho, find the equation of that sphere. It ends up being this. And again, really healthy exercise. Make sure you can do this, right? There's effort, thoughts, challenges, landmines of trig that come up in those calculations. Make sure you're good at that. Okay, how are we doing? Okay, so that's integrals and spherical coordinates. Just like previous coordinate systems, different details, different geometry, different kinds of slices. But it's it's sort of a different version of the same, ultimately the same strategy. Okay, don't forget your stretching factor. Okay, so new question. We're moving on to, this is, I forget the numbers. I want to say this is 14.8. Of course, we've been bouncing around quite a bit inside this sort of third, fourth of the course. And so this is our last section in chapter 14. Due to bouncing around. This addresses a really new kind of question, and that is we want to define a new kind of an integral in a different context. Quick summary before we see what's new about these kinds of integrals. Let's talk about kinds of integrals we've done already. So way back when you studied single variable integrals. They're defined on intervals on, let's say, the x-axis. They're one-dimensional domains sitting inside of a one-dimensional world. Okay. Next thing that we did in this course, double integrals. A two-dimensional domain sitting inside of a two-dimensional world. Triple integrals. A three-dimensional solid domain sitting inside of a three-dimensional world. Right, now we've also talked about a bunch of different techniques. Spherical coordinates is really just a technique for how to compute triple integrals. Polar coordinates is just a technique for computing double integrals. As far as the integrals themselves go, we've seen three kinds of integrals so far. Single, double, triple. Okay. So what we're addressing here is a really importantly different kind of a problem. Let's suppose that I wanted, for example, to look at this curve. Maybe that curve tracks a wire, a metal wire, kind of like a metal rod that you all saw in Calc 1 classes. But this one's all bent and twisty inside of two dimensions, and I want to, and maybe density is non-constant. Mass per unit length depends on where you are in space, somehow. Right? How would you compute the mass of that? Well, is that a double integral? Because look, I'm in two dimensions, right? I live here in two dimensions, but it's not a double integral because when you take slices, all you get, you could try to do a kind of a two-dimensional slicing process, but it remains that all you get as your slices are little pieces of length, not area. That's not a double integral. You can't address that situation with a double integral. It's also not a single variable integral, as we have the problem addressed here. So this is something new. We've never seen this kind of thing before. Analogous problem. What if the curve is going through three space? Well, it's not a triple integral. It's not a single variable calculus integral. Arguably weirder. What if you have a two-dimensional surface sitting inside of three-dimensional space? Well, it's not a triple integral because pieces don't have volumes, they have areas. And it's not a double integral because, well, it's bent and curvy in space. So these are going to be new kinds of integrals. When we address a Riemann sum, if I have some, I want to compute the mass of this thing, I'm going to be doing a chop it up, add it up, approach, but with very different details as follows. On each little piece, so here's my curve. I'm going to chop it up into little pieces. And on that little piece, if that represents a little piece of, bent wire or rod or what have you, non-constant density, the mass that I'm interested in, or whatever quantity is, that I'm adding up, is going to be quantity per unit length times length. Right? Length being the size in question, not area. And Okay, that seems a lot like a Calc 1 integral. Trouble is, do keep in mind, I'm not adding up as a single coordinate goes from, like A to B. I'm adding that up over an entire curve. So this summation is a fundamentally different, at least how we're looking at it here, is a very different kind of summation. Okay. All right. Likewise, over here, if you're looking at a surface in space, if this represents some piece of mass, there's a bent sheet of alloy metal of some sort, right? That's makeup changes over location. And if you want to compute the total mass, well, on each little piece, on that little piece, how much mass, for example, is there inside of there? Well, we're going to look at mass per unit area times area to estimate mass in that little piece. And then, again, we want to add up, but we're adding up in this very, very different way. We're adding up over the surface. Okay, yeah?
This delta S, what is that measurable change?
So it's not, don't think of it as a change, we want to think of it as a size. Right, so this is one of the transitions that we made, when we first started talking about double integrals. But sort of one of the convenient things about single variable calculus is that you can think of delta x in these two different ways. You can think of delta x as how much did the coordinate change. You can also think of it as how big is this little piece, how big is that little subinterval. So same deal here. We want to think of delta s as representing a size. Just like we did with double integrals, we were looking at little pieces of size as area. And so it's just not a change. Yeah. Right. Okay. So in Math 212, we're not going to get into the details of how to define this precisely. What's important to take away about these new kinds of integrals, I'm going to call them, is that we're looking at chop it up, add it up. As a strategy, and this is how you would, very loosely anyway, represent the results of this chop it up, add it up sort of a strategy. A little bit of notation in the same way that a limit and a summation, in the past we've represented that with an integral symbol. In the past we've rewritten deltas as d's. Right, whatever functions on the inside, you put that on the inside. The very plausible notation that we have for this brand new kind of Riemann sum is this. And again, brand new. We've never seen this kind of integral before. It's not a Calc 1 integral. It's not a double integral. It's not a triple integral. It's a new thing, and we don't know how to compute it yet, which is a little scary, right? All our previous integrals, we just did pretty much fundamental theorem of calculus multiple times, perhaps, but we don't know how to compute that. Nevertheless, this notation represents this strategy for computation. Likewise, here there's a limit of a summation that's happening over a area, so there's going to be kind of two indices in some sense, and so we use we're going to steal from our old double integral notation to represent that. Okay. All right. Now, how are we going to compute these things? I have bad news and good news. We'll start with this one, by the way, how we're going to compute terminology. This is called a line integral. The terminology is a little unfortunate, right? Because line we think of as straight lines, but here in this context, forgive the awkwardness. Arguably, it should be called a curve integral, right? Or sometimes it is called a path integral, and that's nice. But more commonly, it's called a line integral. But it just means an integral over a curve. Okay. And likewise, this is called a surface integral. It's very reasonable. Okay, and I'm going to come back and talk about that terminology again in a little while, a few days, but for now, I'll just let that be. Okay, so how do we compute these things? Here's the big complaint that I have in trying to compute this expression, for example, and that is I don't like this domain. It's all curvy and stuff. I don't know how to deal with that. How do you deal with curvy domains? Oh, wait a minute. When have we had that thought before? I don't like this domain. Wouldn't it be nice if my domain weren't all curvy and stuff? Can I rewrite my integral over a different domain. We did exactly that when we did change of variables. This is different, of course, but this is not morally that. This has got all the earmarks of our previous scenario of, hey, we want to change our domain. And so we're going to do it, we're going to approach it in the same way. We're going to view it as the image of a nicer domain that I like, and we're going to do a pullback. Just like we did with change of variables. It's a real ripoff of what we did with change of variables. Again, I have to worry about the stretching factor, right? When you take a domain and push it forward through a change of variables like function, little pieces might get stretched out. So I got to figure out what's the relationship between the areas over here, areas, curves, lengths, whatever, over here versus over here. Maybe some sort of a stretch out factor. Gonna have to figure out what that is. But other than that, pull back. And this is going to work really nicely. Quick observation. The book makes some choices about how to order these topics. You may be expecting, very reasonably, that we would do this first for curves. And then after we've dealt with curves, then we would move on to doing it for surfaces. That would be a very reasonable thought. For whatever reason, the book doesn't do it this way. The book wants to start with surfaces. Sure, whatever. It doesn't matter in some sense. I just want to point out that this does seem like a little bit weird. I like to be able to use curves as kind of a segue, as kind of a stepping stone to understanding the surfaces. So I'm actually going to do some of this development of line integrals first. Then we'll wait. The book doesn't get around to it until chapter 15. So we'll wait on the details. But I want to show the strategy of how to deal with this first, and then from that, that'll segue very nicely into how to deal with the with surfaces. So anyway, it's going to be a little out of order, more so in the book. So here we are. We are in, let's start with 2 space, not that it matters. We have a curve in space. Maybe I want to compute the mass on that curve, or the number of ants crawling around on that curve, whatever. Mass density per unit length, population density, per unit length. I want to do a chop it up, add it up on this curve. Don't like the domain. What am I going to do if I don't like the domain? I'm going to view it as being the image of something that I do like, right? And notice that viewing a curve as the image of a function is something we've done before. That is just a parameterization. We already know how to view these curves as images. So this goes way back to chapter 12. So if necessary, in fact, I would say, as I would expect to be likely, maybe you've kind of forgotten some of the details about parametric curves. This would be a great time to go back and remind yourself. We have 5 minutes left until spring break, so over spring break, remind yourselves about parametric curves. Anyway, with that in mind, parameterize the curve. Here's some details. Keep in mind what I want to compute. What I need to get my hands on is ds. What's the length of a little piece of curve there? How am I going to look at this little piece of curve? By the way, my curve's going along like that. I've got some long curve. I'm looking at just a little piece of curve on that one little piece of curve. How do I compute the length? The short version would be able to say that ds is vdt, and this is a familiar old concept we talked about. Distance equals speed times time. Right? V, speed, magnitude of velocity, just says distance per unit time. So distance equals speed times time. Okay. That gets the job done, but my goal here is to segue into the higher dimensional version. So let me drag this out into a little bit of detail for analogy purposes. To understand this length, what I really need to understand is that position differential vector dx. Again, flashback to chapter 12. We talked about the dx vector. way back when. And it's just the vector that represents our linear approximation based on what's going on that point. What is the linear approximation to our displacement? Right? So how much did position change? Dx is a vector. It's not a scalar. It's not a length. It's a vector. Right? Okay. How am I going to understand? How am I going to understand the dx vector? I'm going to understand that by looking at its coordinates. I'm going to look at, how much did x itself as a coordinate change, and I'm going to look at how much did y as a coordinate change. And good news, those are really easy to understand. We have an input changes, output changes kind of a situation here. When t changes by a little bit, as an input, x and y coordinates are outputs, and the relationship between input changes and output changes is the derivative. So dx dt, dy dt. And that's again, fundamental point of view on derivatives. They relate input changes to output changes. And if you know those two coordinates, the dx scalar and the dy scalar, those make up the dx vector. And the dx vector is the thing whose magnitude gives you ds. And, calculate, and then the happy punchline is exactly what we already knew. It's speed times dt. The point here is not the conclusion. The point is the breaking down of understanding the curve by the displacement vector, understanding the displacement vector by the coordinates, and understanding the coordinates by, single variable derivatives. Okay. All right. Let me spike the football before we go on to the next thing. I have a minute and a half. I think I can do this. Line integrals, we needed to understand. The biggest challenge was understanding our differential. I needed to know how much does that differential get stretched out. There it is. There's our stretching. What do you multiply by dt to get ds? Speed. So there's our stretching factor, and for doing line integrals, that's our new stretching factor. And then you pull back and notice that we have a single variable integral. This is a math 111L single variable integral from A to B, plug and chug. All right. So a quick little preview of what we're going to do in the once we get back from spring break is what's the surface equivalent to this? If I have a parametric surface, so a function that takes an input region in the UV plane and by way of plugging into this function creates a a surface in space, right? Can I do the same kind of thing? Can I keep track of, how does this little piece of area get stretched out by this parameterization to make this maybe a little bit bigger, maybe a little bit smaller, stretched out or possibly squished piece of area? And what is the stretching factor there? And we're going to break it down in very similar ways. And I'm out of time, so y'all have a great spring break, and we'll see you in 10 days. Have a good one. Give me 2 seconds here. Let me just